Good morning, friends. As I talked in the fundamentals of lasers part first, that I will start with the comparison of 3-level laser system with 4-level laser system. So in this second part, I will start from here. Here we can see that a 4-level pumping scheme, laser scheme is actually more efficient in establishing the condition of population inversion as compared to the 3-level energy system. So as to compare these two systems, I have shown in this first diagram 3 energy level system. E1 is representing the ground state, that is the lower laser level. Also E3 is the upper excited state, and E2 is the another excited state, which is also a metastable state. So metastable states have longer lifetimes compared to this E3 state. So here after absorbing photons by the pumping process, the atoms of the active medium will be raised to this level E3, and then since here the lifetime is small, of the order of 10 raised to the power minus 8 seconds, so these excited atoms will decay to the metastable state and through non-radiative transition. So there will be no laser emission, no light emission during this decay. Now this metastable state has a longer lifetime, so an accumulation of atoms will be occurring in this state E2, and then if number of atoms in this ground state is N1 and number of atoms in this state is N2, then to create the condition of population inversion, N2 must be greater than N1. So in this case, this ground state is actually this lower laser level is actually the ground state, and since ground state is generally heavily populated, so N1 is large always here, so N2 must be even greater than that for the condition of population inversion. So in this particular case, that is in the 3-level system, intense pumping is needed so as to make N2 large compared to N1. Now let us see what happens in this 4-level energy system. In this 4-level energy system, E0 is representing the ground state, and E1, E2, E3 are the 3 excited states. So by pumping, atoms from this ground state are raised to this uppermost excited level E3, and since this is excited state, so atoms will stay there only for about 10 raised to the power minus 8 seconds. They will decay to this level E2 through non-radiative transitions. Now this E2 level is the metastable state, so it has a longer lifetime of the order of 10 raised to the power minus 8 seconds. So this N2 is now building up, number N2 is increasing here. So and then this N1 is basically an excited state which is short-lived. So short-lived means whenever here are atoms, these atoms will stay only for 10 raised to the power minus 8 seconds, and then they will jump to the ground state through non-radiative transitions. So effectively N1 is very small because this state is continuously emptying itself, since it is not the ground state, whereas in this case it was the ground state. So population N1 was quite large here, but in this case N1 will be very small, nearly zero, because this state is not the ground state, it is actually an excited state. So this N1 is very small number, and because of that N2 will be almost always larger than N1. So the condition of population inversion is quite easier to establish in case of this 4-level system as compared to this 3-level system. I have shown here the example of laser also which utilizes this 4-level energy system. One example is ND-YAG laser, and another example is helium neon gas laser. So ND-YAG here represents the neodymium doped yttrium aluminium garnet. Now here, as we know, there are 3 important components of a laser. The first important component is the active or gain medium, whose atoms are to be raised to the higher level so as to return back to lower energy levels for laser emission. And then the second important component is a mechanism, some kind of mechanism which is used for the pumping of these atoms of the active medium, or to raise the atoms of the active medium from lower level to the higher or excited levels. So that is the another component. And the third component is the optical resonator or cavity. So this cavity is basically made up of 2 mirrors, M1 and M2, out of which this mirror M1 is 100% reflective. So any of the photons which are moving towards this mirror M1 will be completely reflected back in the cavity. So there is no transmission of photons in this direction. Now this mirror M2 is made deliberately partially reflective because and partially transmittive, partially reflective and partially transmittive because it has to work as the output coupler also. The laser beam has to come out of this mirror whenever the gain inside the cavity is greater than the losses in this cavity. Now we have to understand what is actually the gain and what are the various losses that may occur inside this cavity. So different of losses that may occur inside this cavity are actually the mirror losses, absorption losses and scattering losses. So different kind of losses may be there. So some of the photons that are emitted may be absorbed, some may be scattered, and some others may be absorbed by these mirrors. So the gain of the number of photons which are multiplying in this cavity, this gain should always be greater than the losses in it, so that a sustained population inversion condition is established or achieved. Only then lasing action will take place. So below threshold there will be no lasing emission, laser or lasing activity, and only after the threshold condition has been achieved there will be lasing emission. Now this cavity has 2 kinds of modes. First type of modes are known as longitudinal modes, and the other type of modes are known as transverse electromagnetic modes. These longitudinal modes are actually which fit inside this cavity, for which the wavelength of these modes is actually related to the length of the cavity by this relation L equal to n lambda by 2, where n is integer. So only those wavelengths will completely fit inside the cavity for which this expression is satisfied. So these longitudinal modes are the modes actually which determine the frequency of the emitted laser light or the color of the laser light. Now this mirror M2, which is actually working as an output coupler also, establish the condition that sustained population inversion is maintained and a controlled fraction of the circulating light escapes out through this mirror as a beam of laser. So only that amount of light will escape out of this mirror which do not disturb the sustained population inversion inside the cavity. Not all the light emerges out of this mirror always. Now here I have shown different types of pumping mechanisms or different types of mechanisms used for establishing the population inversion condition. So these different population mechanisms, pumping mechanisms are actually used for different types of lasers. So in case of Ruby or ND-YAG lasers, optical pumping is used. So a xenon or argon flash lamp shines intense light over the active medium, and the atoms of the active medium are raised to the higher level, and which then emit laser light. So in case of Ruby and ND-YAG laser, optical pumping is used to create population inversion. Whereas in case of gaseous lasers like helium neon or CO2 lasers, electron collisions electrical discharge is actually used for the mechanism of population inversion creation. So this electrical discharge will give rise to electrons, and these electrons will collide with the atoms of the helium, and these excited helium atoms then lose their energy in making resonant elastic collisions with neon atoms, and the population inversion is created between the levels of neon atom. So helium atoms has the role of exciting the neon atoms only, whereas the laser emission will take place between the levels of neon in case of helium neon gas laser. So electrical discharge is the pumping mechanism in case of gas lasers to produce population inversion. Similarly, in case of semiconductor diode laser such as gallium arsenide diode laser or indium phosphide diode laser, forward biased PN junction injects electrons and holes, and these injected electrons and holes then recombine, and the loss of energy is then produced as photons. So in this case, current injection is used as a mechanism for population inversion creation. In case of chemical lasers, for example, chemical hydrogen fluoride laser or chemical deuterium fluoride laser, chemical reactions directly produces excited species. And then in case of specialized high power lasers such as high power excimer lasers or high power semiconductor lasers, high energy electron beam excites the atoms of the active medium, and then these atoms will give rise to the laser emission. This we have already discussed. Atomic or molecular collisions between helium atoms and neon atoms. Helium atoms which are excited then transfer their energy to neon atoms, and neon atoms then give rise to laser emission. Here I have shown some of the laser families: gas lasers, solid state lasers, semiconductor lasers, liquid or dye lasers, and fiber lasers. And then what are the different active media for these type of lasers, and what is the pumping mechanism. So for example, for helium neon laser, which is a type of gas laser, the emitted wavelength is 632.8 nanometer. In terms of angstroms, it will become 6328 angstrom. So this is actually the bright red color. So I have tried to show the color of lambda by the color which is actually emitted by this gas laser, helium neon laser. Then another type of gas laser is CO2, and another one is AR+. So we have already seen that this gas lasers have electrical discharge as the pumping mechanism. Similarly, for solid state lasers, whose examples are Ruby laser and ND-YAG laser or ND glass laser. Ruby laser emits a light of wavelength 694.3 nanometer. Again, in terms of angstroms, it will become 6943 angstrom. Now this is the light of deep red color. So Ruby laser emits light of deep red color, and in this case xenon or krypton arc lamp is used for optical pumping. Then in case of semiconductor lasers, whose examples are shown here: gallium arsenide, indium phosphide, aluminium, gallium arsenide. These are the active media. So in this case, visible light is not emitted. Actually, these are infrared lasers. So in this case, a forward bias PN junction is used as pumping mechanism for the laser emission. Then for the case of liquid or dye lasers, rhodamine dyes are actually the active media, and optical pumping is used for the creation of population inversion. Then there are some fiber lasers also. These are actually the rare earth doped optical fibers, and these are basically these utilize the optical pumping for establishing the condition of population inversion. So laser is actually you can say stimulated emission plus some kind of population inversion, plus suitable energy levels, and plus optical feedback. So these are four basically components to give us laser light, and that laser light is actually coherent, nearly monochromatic, highly directional, and often very intense light. So we get a laser light by utilizing these conditions. Now here in the last slide I have shown four different numerical problems which will actually give you a feeling of some numerical things associated with this laser. So here I have given one photon from a ruby laser, which is actually emitted at a wavelength of 694.3 nanometer, and here you are asked to calculate the energy of this photon. So it is very simple. You can calculate the energy by using the relation E equal to hc over lambda. So lambda is first converted to meters, and then we will get energy of the photon by this numerical value 2.86 into 10 to the power minus 19 joules. In the second problem, helium neon laser emits light at 632.8 nanometers. Its frequency and photon energy is required in this numerical problem. So frequency and wavelength are related by this expression, nu equal to c over lambda. C is the speed of light, so you can easily calculate from here the frequency, which will come out to be this value, and similarly then E equal, by using this relation E equal to h nu, you can also calculate the energy of this emitted photon in case of helium neon laser. Now in this third problem, the number of atoms in the lower laser level and the upper laser level are shown. Then the ratio between these number of atoms is required here, n2 over n1, and in the second part, what is the fraction of atoms in the upper level. So two things are to be calculated in this numerical problem. First one, n2 over n1 is a direct calculation, and for the second thing, to calculate the fraction of atoms in the upper level, we have to calculate n2 over n1 plus n2. What are the number of atoms in the upper level as a fraction of total number of atoms. So this will be this will come out to be 80%. And finally, in the fourth problem, Einstein's, which is related to Einstein's coefficient, frequency is given, B21 coefficient is given, and you are asked to calculate the coefficient A21. So by using this relation, you can easily calculate the Einstein's coefficient A21. So this was the second part of laser, and so far we have discussed the fundamental concepts related to lasers. What is actually a laser? What are the various components of a laser? That is the three main components: active or gain medium, pumping mechanism, and the optical or optical resonator, that is the cavity. Then we have also discussed the properties of laser light and how it is different from the ordinary light, because laser light is highly coherent, highly directional, nearly monochromatic and is often very intense and sometimes polarized also. And we have also seen that at least 3 energy levels are required to create the condition of population inversion. We have also seen that a 4 level energy system is relatively easier to calculate to maintain the population inversion as compared to the 3 level energy system. We have also seen that what are the components in this optical resonator cavity. So in the third lecture I will discuss about the comparison between the pulsed laser and continuous wave laser. So till then, thank you. I hope you will enjoy this lecture and the previous one also, and we will shortly share the third lecture about lasers. Thank you.